When people think of building a colony on Mars, they usually focus on the process of getting there, of launching the rocket, spending months in space, and planning out the Martian habitat. But once we get there, what happens next? What will daily life for the Martian colonists actually be like? I believe that the success of a Martian colony ultimately depends on its food, from growing to cooking to eating. But what types of foods will actually be successful on the Red Planet? What kinds of cuisines will the Martian colonists prefer? And what will we actually be able to grow and cook in an environment that is quite literally totally alien? I'm on a quest to find out. With the goal of engineering the Martian menu, I'm bringing together scientists, engineers, historians, and chefs to ask one simple question. 50 years from now, what will the average Martian colonist eat on an average day? I'm Sarah Gilbreth, and this is the Martian Street Food Society. Today, I'll be laying the groundwork by looking at some of the foundational forces on Mars that differ from Earth, like gravity and atmospheric pressure. We'll be talking to a range of experts to discuss how those forces will impact Martian food from the farm to the table. As always with science, we're not asking questions to get us immediate answers. We're asking questions to get us better questions. Initially, the Martian colonists will likely be eating pre-packaged food from Earth, but for any colony to be successful, eventually they're going to need to start farming, which brings me to the first category, growing food. Farming on Mars presents a number of challenges, most notably water and the chemical composition of its soil. Now, I want to pause here for a second to talk about the term soil. That term, by definition, includes organic matter. Mars doesn't have any of that, so instead, the term regolith is used. But what other differences are there between soil and regolith, and how does that affect what we can plant there?
Hi, I'm Zach Martellucci. I'm a science communicator and educator, and I've worked in museums and botanic gardens around the world. I'm super passionate about ecology and plants and the way our Earth's systems allow life to thrive.
My name is Brandy Cannon, and I am a 8th grade science teacher. I am also the middle school curriculum coordinator. My background is in botany. I did my undergrad and my master's focusing on parasitic plants because that is what I truly love to research. We all take different paths in our road of science, and this is where I currently am. But actually doing a lot of this research on like astrobiology is like really neat. So I kind of like the niche projects of science and botany.
To start, we need to know what plants need to grow successfully. Generally, plants grow well in soil made of some combination of organic matter, water, air, and mineral materials. Specifically, the minerals they need are nitrogen for healthy foliage, phosphorus for flower development, and potassium for root growth. Does Mars have all of that? No, not really. Mars' regolith has no water, little nutrients, is much more iron-rich and has plenty of hydrogen peroxide, and isn't quite as airy as the soil on Earth.
To date, no actual Martian regolith has been brought back down to Earth. However, the data that we've collected shows that there will likely be high levels of sodium, potassium, chloride, and magnesium. Now, some of those are great. That's exactly what plants need. The others, however, not so much, and that could present a major obstacle.
The magnesium and the potassium is fantastic. That's what you usually find in your fertilizers when you're adding like better things back to your soil. But the sodium and the chlorine are the things I'd be mostly concerned about because most plants are not salt tolerant. Majority of the plants would prefer not to live in salty conditions. And that's because salt makes it really difficult for water to transfer through roots. And that obviously would be the thing that you don't want to happen. There are some salt tolerant plants, but usually they're not your crops.
But that doesn't mean there isn't hope for growing crops on Mars. Multiple independent studies here on Earth have had success growing crops in Martian soil. A study in the Netherlands and another at Villanova University in Pennsylvania successfully grew kale, lettuce, garden cress, rye, arugula, tomatoes, radishes, chives, peas, leeks, hops, and quinoa. Interestingly, they also attempted to grow potatoes, but they didn't survive.
Thanks to the recent movie The Martian, the #1 food that comes to people's mind when they think of Martian food is, of course, the potato. And there have been a number of studies done in numerous different countries about growing potatoes in Martian regolith. But unfortunately, it doesn't look like it's going to be the most successful crop.
The regolith was just too dense and crushed the baby potatoes. Sorry, Matt Damon, looks like The Martian wasn't totally accurate.
So the people who've been doing research on this, they specifically aerate, usually using like vermiculite and their favorite, cardboard, because more than likely you're going to have cardboard with you on, say, the International Space Station or wherever you are. So you could just break that out, reuse it, and put it in there to sort of create aeration.
We can also introduce earthworms. Apparently, in at least one study, they thrived in Martian regolith. The earthworms help to further break down the fertilizers and help keep the soil healthy. Plus, they also had the added benefit of digging tiny tunnels to allow water to reach the roots more easily.
They also use worm poop as a way to aerate. So, you know, you're still keeping those like small gaps and allowing for that sort of transfer of nutrients.
This is all very exciting. Seeing crops grow in Martian regolith is a great sign for successful farming on Mars. However, there are some serious problems that still need to be addressed. It's still hard for us to perfectly simulate Martian regolith here on Earth. You can't just go out and buy it from the store. So we have to make our own.
Now, since none of the Martian regolith has actually managed to make it down to Earth, that means that all of the scientists that are conducting these farming studies have basically had two different options. One, they could buy something called a simulant. Now, this is something that simulates Martian regolith. It's not exact, but it's pretty close. Or two, they could make their own regolith at home by mixing together different kinds of soil. And if you've ever wanted to do your own Martian farming experiment, good news, you can.
That Villanova study I mentioned made their own regolith by taking volcanic basalt and mixing it with other compounds to make it about 90% similar to what is found on the red planet.
Within the soil, just like looking through people trying to recreate Martian soil, which is really cool, by the way. When they recreate it, you find that it's so densely compact because of the sand and the clay-like behavior that basically you're probably not going to get any of that gas exchange that you normally would. And that's usually really important for microbes. And microbes are the reason that your plants do so well in soil to begin with here on Earth.
Martian regolith has no organic matter and little essential minerals. To solve this, we'd have to introduce them ourselves. Thankfully, a few companies here on Earth already make Martian fertilizer that we could bring with us. Or if we didn't want to bring it with us, we'd have to figure out a way to introduce the organic matter and essential minerals from the stuff that we already have with us. Which, if you think about it, would just mean using our poop.
Now, it's easy to focus on the things that are missing in the Martian regolith, like organic matter, but there are also a few things that are present in the regolith that could cause some problems.
There are other minerals in Martian regolith that are harmful to humans. The main harmful chemicals are perchlorates, which are super abundant in the uppermost layer of Martian regolith. When perchlorates are exposed to UV light, which is inevitable with Mars's thin atmosphere, they can create some pretty harmful side products. These side products can cause thyroid problems and even death. So growing crops in this soil is hella dangerous. Sorry again, Matt Damon, you'd probably have died if you didn't deal with the perchlorates in the soil. Thankfully, there are ways to remove the perchlorates. One way is to simply rinse the soil, since perchlorates dissolve in water. That would be a huge task, but it could save some lives. Another option is to use perchlorate-eating bacteria to get rid of the perchlorates. Plus, they'd have the added benefit of producing oxygen as a metabolic byproduct. While it might seem like growing crops on Mars is a real shot in the dark, it turns out that we have a lot of resources to make it work. So while Matt Damon wasn't necessarily doing it correctly, he was on the right track. Obviously, there are a lot of things to figure out still in Martian farming, like access to water and light and growing viable seeds. But these studies and solutions show us that Martian regolith might actually be more ready for plants than we originally thought.
In order to find out what crops grow well on Mars, the first step is finding areas on Earth with similar climates and soil composition. We can then use those areas as comparisons, or analogs. The most recent data shows that the Martian regolith is very heavy in basalt, similar to volcanic soil on Earth. That helps us narrow down the amount of analogs that we have to work from.
Basalt or volcanic soil only takes up about 1% of the entire Earth's like sort of soil composition. But there are lots of countries and cities and states that are very populated that really rely on the soil. I was checking in Rwanda, which is one of the highest populations, they grow all sorts of stuff. So like maize, potatoes, sorghum, which is really popular, peas, bamboo and eucalyptus and like daisy-like flowers. So you really actually aren't limited because this volcanic soil is so fertile. It has so many minerals and nutrients that you would want to have, actually probably better than some of the soil you would get in like maybe your backyard, your standard backyard. But really, it seems like volcanic soil actually is not the limitation of growing plants on Mars.
The really great thing about this new research is that it's leading to the development of new products that could be used on Earth that we otherwise might not have ever thought about.
I read this one study where a PhD student at University of Hawaii was using cyanobacteria as a way to sort of, because it grows basically anywhere. Like we're like taking samples off of the International Space Station, which is really awesome that you can keep it outside in space, which means that you can absolutely like take it, replicate it, genetic engineer it, and incorporate it into your actual soil. So those things are the things that those microbes are so essential to like breaking down products in the soil and in the fertilizer to give you back the nutrients that you want. Otherwise, you're sort of lacking the nutrient cycle that microbes normally do for you. We were actually trying to see if it grew out in space. They had it on the outside of the space station, which is like kind of nuts, right? Like this bacteria that could really solve a lot of problems was growing outside of the space station. They could just go out and swap it and bring it back in. So I thought that was really neat and some really interesting work to show that you don't necessarily have to focus on fertilizer, but that you can use bacteria that you find or that you bring or that sort of thing. Obviously, we have to be careful because we don't know how bacteria would work in certain environments in Mars, but that is a potential greenhouse solution. So higher altitude climates on Earth there's a variety of things that's going on there. And with a higher altitude, you usually have a different climate. It's cooler, it's thinner, you're getting much more solar radiation because you're closer to the sun. You're also dealing with both dry and wet climates. I would say there are different plants that can manage to grow up in higher altitudes, but you have to consider what's the sunlight going to be and is it going to be too much for those plants, especially plants. So when there was a study that was focusing on Martian plants and they realized that they had to reduce the amount of sunlight because Mars receives less sun than Earth because it's further away from the sun. But they realized that they can't grow full sun plants. And that's like a huge deal, right? Because a lot of our full sun plants are things that you would absolutely want to eat. When you're thinking about further up, you have to think, can they deal with thinner atmosphere, cooler weather, and more harsher UV radiation? You want to think cool season plants like lettuce, cabbage, things that are lower to the ground. Root vegetables usually can survive, and herbs, but they really need to be hardy tolerant because climate and weather can be so drastic on sort of like high elevation in mountains because of that wind and that atmospheric conditions. Considering, I would say, and this is silly, considering that Martian soil is so like clay-like and dense, and even when you aerate it, you still have to be a little worried about your plants drying out. It would probably be really difficult to overwater. So, and I am someone who often forgets that I haven't watered in a while and I need to go back and water. But if I water too much, I'm like, oh, I'll leave it there for a bit. So this is something that, you could just water every day and not have to worry about, am I missing out? Am I giving it too much water? Am I giving it too little water? So I think that's a benefit for people who don't necessarily have a red thumb, is watering every day and not being too worried about killing it by overwatering it. I don't know if you've heard of, at Villanova, they have this program that's called the Mars Garden Project. It's basically this professor who's been working with the students since 2017, and every year he gets his undergraduates to conduct Mars plant growth research, and it's really cool. They do it every year, but they're trying to like fine tune it more and more every year. Probably the other thing that I would mention, fun fact, is that you can buy like Mars regolith online. So if you wanted to conduct your own experiments, you totally could, and see if like you can like get some things to grow and like manipulate it yourself. I think right now this is obviously people are sort of looking towards the future in Mars because it's not looking great on Earth, but it'd be interesting to see sort of where independent research beyond academic institutions sort of plays in this like next step for mankind kind of thing.
I saw the botanical garden in Chicago. They posted, this was a couple of years ago, but the internet is forever. They posted a recipe for how to mix your own Martian regolith at home.
Yeah,
Yeah,
I saw that. I thought that was really cool. I wish they had updated because I wanted to know how her experiment went. But it's an easy experiment to even get kids involved with, right? Like I'm always looking for something that I can sort of take to my students and say, we're going to do this, and it's up to you to sort of figure out what you want to do specifically to manipulate. And they get really into it, and being able to tell them, you're on the frontier of this sort of research, and you don't have to wait until college. So it's definitely, it leaves room for growth. That would be the other answer I would say about the benefit of going to Mars and trying to grow plants, is that no one else has done it before, like actually done it. So there's lots of room for error, but there's lots of room to make new discoveries. And that is usually the best part about science.
Plants grown on Mars will likely be grown inside biospheres. Now, this will give us some control over the atmosphere and air pressure. But one thing we can't control? Gravity. Gravity has a huge impact on the way plants grow, from the height of the stalks to maybe the depths of the roots. Another thing that gravity impacts is the flow of water. Now, Mars's gravity is only about 38%, or slightly over 1/3 of what it is on Earth. That may not be strong enough to rely on traditional Earth irrigation methods.
My name is Kaylee McCluskey. I am a biophysicist, which means that I'm a physicist by background, and I study kind of systems at the interface of physics and molecular biology. I actually study the way DNA is replicated. In many respects, it's what makes liquids flow, right? I mean, what is the principle of how water flows and how rivers form on the surface of the Earth? Water begins high, it begins in mountains, it begins with a spring or with glacial runoff or whatever, and it travels down. Gravity pulls it downward through whatever the lowest points in the land are, and it collects into rivers and then lakes, then flows ultimately towards the ocean because gravity is pulling it. Nothing else is pushing it. So Mars has what, 1/3 the gravity of Earth?
38%.
38, yeah, 38%. Yeah, so that means water will still flow. It'll still travel along surfaces. It'll still collect in the lowest point, but gravity is only 1/3 as strong. It goes 3 times slower. It probably collects more easily along the way. So like with farming, you might end up with, it might be harder to drain land, right? Because the water doesn't flow off as easily. You have a shallow gradient, and on Earth, the water would flow along it, but only 1/3 the force of gravity pulling on it, it might stagnate more.
Obviously with like microgravity, your water doesn't act the way you want it to. It's like once you've got everything solved, it's like, oh, and the water's dripping left ways rather than like straight down. So that is absolutely probably a really cool, man, that would be really neat to do like a centrifuge water simulation, but that would definitely be an issue that you'd have to solve, especially for deep roots, like tap roots, like things like carrots. They would need water to actually trickle all the way down to really sort of manage them and make sure that they don't end up being like these little pencil-shaped vegetables.
When we think of eating in space, one of the first images that we think of is of the astronauts on the space station with food floating all around them in the air. Now, obviously, that's in zero G. So, on Mars, would soup be able to stay in the bowl or would it float out? What percentage of gravity do you have to have for food to start floating out of its pan?
Probably 0 or really close, yeah. I mean, I guess if you were at like 10% gravity or something and you like pulled the bowl away really fast, then the soup would be like, because it would still fall, but it will fall slower. But on Mars, like in a dome on Mars, your issue would be the air pressure more than the gravity. Because you'll probably have low air pressure, and that is a lot like being at a high altitude. The equilibrium between the liquid phase and the vapor phase is tilted a little bit more towards the vapor there, so the water will boil at a lower temperature. That'll be far, far more due to the pressure than the gravity. Think about the kind of biosphere of Earth as a whole. We've got lots of liquid water, lots of gaseous water, and lots of water in the ice. We got lots of ice, all coexisting at the same time, basically in one big spherical box, which is the Earth. So there's, at any temperature and any air pressure, there's an equilibrium between these three. It's not just that, you know, at 75 degrees Fahrenheit, all water has to be liquid. There is, you live in the South, there's water vapor in the air. And there is an equilibrium, they exchange. So water evaporates, water condenses. If there's a temperature differential between two surfaces, then locally more water vapor will precipitate out into the liquid phase. And as the air pressure, like when you work through the equations for this, they depend on pressure, they depend on temperature, they depend on the density of what you're talking about, in our case, water. And as you decrease the air pressure, then you'll get a change in the equilibrium. More water can evaporate into the air. It can hold more, basically. So, you know, you go up on a mountain or into an airplane cabin or into a dome on Mars, your air pressure is going to be, you know, maintained such that it's livable, but it will probably be lower than sea level on Earth. I mean, maybe not. Maybe you'll make it more higher pressure. I don't know. But assuming it's lower, I assume that it will be lower. It'll be easier to boil water. It'll boil at a lower temperature because the lower pressure means that the equilibrium will be tilted a little bit more towards vapor. That's just like being at a high altitude on Earth. And something interesting I had pointed out to me not too long ago that actually really does affect the way you cook foods in terms of food safety. Because we tend to think, you know, as long as we boil the water, it's hot enough that it will kill all of the bacteria. But if it boils at a low temperature, then actually, if the temperature is low enough, then you think your food is cooked, but you've never actually gotten it to a high enough temperature to kill everything. I think this happened, I learned this tidbit while watching a documentary about a guy trekking through Tibet, I think. And he had to be really careful about how he cooked his meat because he would think it was cooked, it would look cooked, it would taste cooked, but the temperature he was using was so much lower, unless he was really careful, that he could give himself food poisoning because he hadn't killed everything yet. So you need to be aware of that. You need to be aware of how hot your food gets, because maybe on Mars, that kind of intuitive, oh, it's boiling, it's hot enough, that might not be true. You have to check.
But that lower gravity will still have an impact on the cooking process. Small, lightweight ingredients like flour or sugar might be more difficult to work with. Astronauts have been facing similar problems on space missions for decades. Small particles like salt or breadcrumbs would go floating through the air and get stuck, potentially damaging multi-million-dollar pieces of equipment. NASA's solution? Suspend those particles in a liquid like water. Get it? Solution? They would also coat dehydrated foods with gelatin to stop them from forming crumbs. If you've ever purchased space food from a museum or a space center, that's the kind of waxy film that you taste on the outside.
Equilibriums are going to be weird. It's like stuff that wouldn't act like dust and float around in your kitchen will get kicked up more easily. You know, flour dust that would normally sit on your counter will be more likely to get caught in a breeze and float around in your kitchen because it's lighter on Mars. So there will be some things that don't behave in quite the way you expect, but it's just because they act like they're functionally lighter. So yeah, you'd probably have to worry about like dust and crumbs and powders and stuff getting stuck in places where they ordinarily wouldn't, because any passing breeze will move them a little bit more. but they don't behave in a really alien way. It's just not quite what our intuition would have us expect.